Welcome, this is Harish. This is a practice final for your calculus exam that would take place on 30th of June. I've added most of the questions that are covered in your course, but I've focused on the last topics because they are more recurrent in your final, and that's the theme mostly. And I have skipped over a lot of practical problems that I thought, and in the previous problem sets I've added a lot of practical questions, but I did not for this final. The reason is because that's been the theme with your course, and I don't want you guys to get really overwhelmed by it. But the reality is that you guys need to understand those problems at some point because they are important problems, because you need to use your knowledge of calculus to be able to model physical problems. After all, you guys are doing a degree in physics, so I'd really recommend if you can do that after your exams when your mind is clear. Now, for the questions we have, we'll start with the first question, of course. And this is just an estimation question for an integral. So you guys might know what an integral is. An integral is an area. Now you can always estimate the area of a shape. How you do so matters. Now you can almost always find some sort of a closed form solution to integrals. Not almost always, in most good cases you can do that. But a lot of times you have functions that are not easy to calculate the integrals to. And a lot of times computationally dealing with things, you don't want to know analytical expressions at each step of your way. So you resort to numerical integration. So numerical integration in this case is just a simple estimation of the area through geometric arguments. Now, a function is some sort of a shape. That is where the intuition for integration is built as well, that the integral is the area under the curve on the given interval. Now, how would you estimate it? You can estimate it in a number of ways. Because the function is known in the interval, you can take a number of points or make a number of intervals. In this case, because we have to take 3 subdivisions, so I will add 2 points in the interval at some other values. This will give me a segment like this. So we have 3 segments now, 1, 2 and 3. Now we can go towards the actual problem, which is calculating the actual area under the curve. Now the actual area can be estimated by finding this sort of a rectangular area, okay? Or conversely, you can do this, which is sort of for a monotonically increasing function. It's an upper limit and that is a lower limit, and you can also take an average of it to get a better sense of the value that you want to get. But what we have to use in this question, as you can read, is the trapezium rule. It bypasses both those techniques, and what it says is it just joins the 2 points with a straight line. Now, the type of figure you have right now in each segment is called a trapezium. Now, trapezium has a common width, okay, and a shorter and a longer side. The area of one of these segments, it's a very fairly known geometrical principle, it's called h by 2 a plus b, okay. Now, what would be the area of the full thing? There would be these trapeziums. All of these trapezium areas would be added to get the total integral, or sort of the estimate for the integral, because it would be somehow, if the number of slices are finite, there should be some sort of a discrepancy. Let's just put this almost equal sign. So the area should be h by 2. Everything has the same width, h by 2, okay. Now you can see the first point and the last point are counted once because they're parts of only one trapezium. All the other points in the middle, they are part of 2 trapeziums, the one before, the one after. So that is why there would be a double count for all of those points. So the function at the first point A plus the function at the last point B plus 2 times the function values at all the other points added together, okay. So this is the general formula to find the area estimated through the trapezium rule. Okay, so in our case, as you can see with the table over here, the x values are taken in radian. This is very important point. Okay. The important point is always take angles in radians when calculating and estimating for areas, because radians are the natural units for angles. Okay. By construction, so you have to make sure of that, because if you take degrees or other units of angles, there would be problems in your answer. They would be way off. So we need to take radians here, and we've calculated the function values at these different points. As you know, here the total interval was 0 to pi by 2, which is pi by 2. Divide that into 3 subdivisions, that becomes pi by 6. Therefore you see the first one is pi by 6, and then this is 2 pi by 6. The third one is 3 pi by 6, which is automatically pi by 2. Okay, so I've evaluated the function at all of these values. Now we'll just simply use the integral formula here. H is pi by 6, so pi by 6 by 2, that would become pi by 12. These two values are the n values, and they would be added once, as I've said. 0 plus 1. Everything else that is in the middle would be added twice. So that is very important to note, that everything else in the middle, however many terms there are, you just need to add those twice. This comes from this geometrical understanding that these are trapeziums, as we've already mentioned. So let me just check the answer. I did it. Okay, it was 0.49 something, 0.4907, I think. And the actual answer, although this integral, this function seems like it cannot have a closed form solution, it does have a closed form solution, and the answer that you find from there is 5 by 32 pi, which is almost the same. It's 0.4908. So we get it into a good degree of accuracy.